Recurrent neural networks. Let's go with the introduction to RNNs. RNNs or recurrent neural networks are a class of neural networks designed to effectively process sequential data by maintaining an internal state or memory. They are widely used in natural language processing, speech recognition, time series analysis, and other sequential data tasks. Let's deep dive into the introduction to RNNs. Some of the basic concepts of RNN are sequential data, temporal dependency, and vanishing gradient problem. RNNs are specifically designed to handle sequential data where the order of element matters. Examples include sentences in a natural language, audio signals, and time series data. The temporary dependencies, for that, RNNs maintain a hidden state that captures information from previous time steps, allowing them to model temporal dependencies in sequential data. What is the vanishing gradient problem? Traditional RNNs suffer from the vanishing gradient problem, where gradients diminish exponentially over long sequences, making it difficult to learn long-term dependencies. What is the architecture of RNNs? First one is the recurrent connections. RNNs have recurrent connections that allow information to persist over time by feeding the output of the network back to itself at the next time step. The hidden state. At each time step, RNNs maintain a hidden state vector that summarizes the information processed up to that point. Output. The output of an RNN at each time step can be used for prediction, classification, or as an input to subsequent layers in the network. The types of RNN. There are 4 types of RNN. First is one-to-one, traditional feed-forward neural networks that process fixed size input and produce fixed size output. One-to-many generate a sequence output based on a single input, example image captioning. Many-to-one produce a single output based on a sequence of inputs, example sentiment analysis. Many-to-many or sequence-to-sequence is process a sequence of inputs and produce a sequence of outputs, example machine translation. Long short term memory, LSTM, and gated recurrent units. LSTM or long short term memory networks are a variant of RNNs designed to address the vanishing gradient problem by introducing memory cells and gating mechanisms that control the flow of information. GRU or Gated Recurrent Units are a simplified version of LSTM that also incorporate gating mechanisms but with fewer parameters. Training RNNs. The first way of doing that is backpropagation through time, BPTT. RNNs are trained using backpropagation through time, where the gradients are propagated backwards through the recurrent connections over multiple time steps. Next way training is gradient clipping. To mitigate the exploding gradient problem, gradient clipping techniques are often applied to limit the magnitude of gradients during training. Next training method is regularization. Techniques such as dropout and recurrent dropout can be used to regularize RNNs and prevail over fitting. What are the applications of RNNs? The first one is natural language processing. RNNs are widely used for tasks such as language modeling, sentiment analysis, machine translation, and named entity recognition. Next one is speech recognition. RNNs can process sequential audio data for tasks like speech recognition, speaker identification, and voice synthesis. Another application is time series analysis. RNNs are effective for modeling and forecasting time series data such as stock prices, weather patterns, and sensor data. Recurrent neural networks (RNNs) are powerful models for processing and analyzing sequential data thanks to their ability to capture temporal dependencies. Despite challenges such as the vanishing gradient problem, variants like LSTM and GRU have been developed to address these issues, making RNNs application to a wide range of tasks in the natural language processing, speech recognition, time series analysis, and beyond. Understanding the architecture, training techniques, and application of RNNs is essential for effectively applying them to the real world problems and extracting meaningful insights from sequential data.